Okay, this video is just a quick overview of rational functions. I'll go into more detail on some of these aspects in future videos. We'll start with the definition. A rational function. The word rational in math always means fraction. Anytime you see the word rational, you're talking about a fraction. In particular here, we're talking about a fraction of polynomials. So top and bottom are both polynomials, with the exclusion that the bottom, the denominator, cannot be the perfectly good polynomial 0 because we can't divide by 0. Okay, so for example, this is a perfectly good rational function. The top, y equals x minus 3, just a line, which is a polynomial. The bottom, also a polynomial of degree 3. Okay, rational functions have domain issues. Anytime you're dividing, you have to worry about dividing by 0. So if you have a rational function, any number that makes the denominator 0 cannot be part of your domain. Can't divide by 0. Okay, so to find the domain of a rational function, you take the denominator, set it equal to 0, and you solve for x. But that does not give you the domain. This is a very common mistake. People will take the bottom, set it equal to 0, and think they found the domain. That gives you the excluded values, the things you're not allowed to use. The domain will be everything else except those excluded values. For example, we've got this perfectly good rational function here. If I want to find the domain, I say take the bottom. And here's a way to make sure you don't mess this up. Instead of saying equal to 0, you can say the bottom is not allowed to be 0, which in this case means the bottom is not allowed to be 5. So the domain is all numbers except 5. I can plug in any real number I want here except for 5, because then that would be dividing by 0. Okay, we're never going to stop here though. We're always going to write domain in interval notation, which you should be really good at by now. This domain would be negative infinity to 5, union 5 to infinity, parentheses all around. Okay, here's another example. Perfectly good rational function here. We want to find the domain. All kinds of crazy stuff going on top. I don't care about that. When I'm looking for domain, take the bottom, set it equal to 0, or in this case, not equal to 0. Solve. That's a quadratic, I just factored it. We get two bad guys, 3 and 5. That's not the domain. These are the numbers I'm not allowed to use. X is not allowed to be 3 or 5. So again, we write that in interval notation. You should know how to do this. Here's our domain. Okay, rational functions will often have vertical asymptotes. Not always, but most of them do. The way you find vertical asymptotes is the first thing you do, take your function, factor top and bottom, see if anything cancels. If anything cancels, cancel it out. You'll still have domain issues there, but you don't look for vertical asymptotes until after you've canceled. Then, once you've canceled anything that cancels, any number that makes the bottom 0 gives you a vertical asymptote. But that's just like finding the domain. Finding the domain and finding the vertical asymptotes are the same question. We just write the answers a little differently. So, if you have a function, it's already been reduced. You've already canceled anything that cancels. The vertical asymptotes, the excluded values, same thing. Okay, this is important. Vertical asymptotes are vertical lines. It's kind of built right into the name. They're not horizontal lines, they're vertical lines. Vertical lines are always of the form x equals a number. X equals 3, x equals 12, whatever the case may be. You can't graph a number, and vertical asymptotes are related to our graph. So they're always x equals whatever number we have. a graph can never, ever, ever touch a vertical asymptote. They're like force fields. The graph can get really close to it, but will never touch it. Okay, for example, say we've got this perfectly good rational function here. If we wanted to find the domain, we would take the bottom, set it equal to 0. We could see pretty quickly, we get x equals 2 as the excluded value. So the domain would be negative infinity to 2, union 2 to infinity, parentheses all around. Now, what if we wanted to instead find the vertical asymptotes? Well, we would set the bottom equal to 0 and solve. But wait, that's what we just did. Finding the domain and finding the vertical asymptotes are the same question. The vertical asymptote is x equals the excluded value. The vertical line x equals 2. And this is what the graph would look like. That's our ultimate goal here, is to graph these guys. And that's our first step, is finding domain, then finding vertical asymptotes. So I have this vertical line, x equals 2. And you can see from both sides, the graph gets closer and closer without ever touching this vertical line. Okay, horizontal asymptotes. These clearly will be horizontal lines. Here we're talking about end behavior. Just like we did with polynomials, we want to know what happens on the far left and the far right of the graph. That's what horizontal asymptotes tell us. We want to know what happens for really big values of x. Okay, when we're looking for horizontal asymptotes, there are a few rules you just have to memorize. We look at the degrees of the top and bottom. Okay, here are our 3 rules. You just have to memorize these. If the degree of the top is bigger than the degree of the bottom, you don't have a horizontal asymptote. You have none. Sometimes you'll have an oblique asymptote, but you deal with those in pre-calc. Here in college algebra, we don't even deal with those. If the top is bigger in degree, there's no horizontal asymptote. If the degrees of the top and bottom are the same, you get a horizontal asymptote by making a fraction out of the leading coefficients. And if the top is smaller, if the bottom is bigger, your horizontal asymptote is always y equals 0. Always. Okay, horizontal asymptotes are horizontal lines. Vertical asymptotes are vertical lines. Horizontal are horizontal lines. They always have the form y equals a number, because horizontal lines are y equals a number. A graph can cross a horizontal asymptote. A lot of them do. You can't cross a vertical, but you can cross a horizontal. Remember, horizontal asymptotes are really just end behavior. Anything can happen in the middle. These guys really just tell us what happens on the far left and far right of our graph. Okay, so a couple of examples. Let's say we have this guy here. We're looking for horizontal asymptotes. I look at the degrees of the top and bottom. On the top, degree is 3. On the bottom is 2. So who wins, the top or the bottom? What about that 1,000? Don't care, couldn't care less. I'm only looking at degrees. The top wins. There's no horizontal asymptote. If the degree of the top is bigger, no horizontal asymptote. This is what the graph looks like. There's no horizontal asymptote. Okay, here in this example, degree of the top is 2, degree of the bottom is 2. They have the same degree, so I take the leading coefficients. I get y equals 10 over 5, which is 2. I didn't get y equals 2 here because of the degrees. I got y equals 2 by making a fraction out of the numbers in front. Y equals 10 over 5. Okay, this is a tricky place. You got to be careful here. 10 divided by 5, of course, is 2. Here's what the graph looks like. Notice on the ends, don't care about the middle, on the ends the graph is getting closer and closer to y equals 2, this horizontal line. On this side, the graph is approaching the line from below. Over on the right, we're approaching the line from above. Notice right here, looks like, I don't know, maybe at 1 or 2, at x equals 1 or 2, the graph is crossing over the horizontal asymptote. That happens sometimes. Sometimes you'll cross over a horizontal asymptote. Okay, one more example for horizontal asymptotes. In this example, the degree of the top is 1. On the bottom is 2. The bottom wins here. The bottom is bigger in degree. The horizontal asymptote is the horizontal line y equals 0. And here's what the graph looks like. Let's look at this guy again. If we wanted to find the vertical asymptotes, we already did for something like this, set the bottom equal to 0, we'll get x equals 3 and x equals 5. That's why we have these vertical asymptotes here. There is some graph in between here, it's just off the screen right now. Here's our horizontal asymptote, y equals 0, the x-axis. This graph is getting closer and closer to y equals 0 on both sides. Notice we cross over right here. The graph crosses over the horizontal on this left side and is riding underneath the x-axis on the left, but is riding on top on the right. Sometimes that happens. Okay, the last thing we have to talk about for rational functions is holes. Okay, if you have a number that makes both the top and bottom 0, you don't get a vertical asymptote there. You get a hole instead. So what we do is, anytime we have one of these rational functions, the first thing we want to do is factor everything. Okay, so this guy here, we could factor top is a difference of squares, x minus 3, x plus 3. The bottom's x minus 3, x minus 5. Hey, look, I've got a common factor I could cancel out. X minus 3. So if I cancel that out, I just get what's left over, x plus 3 over x minus 5. But these aren't really exactly the same function. If I cancel that out, remember, you're not allowed to cancel out 0. 0 divided by 0 is not 1. So this is only, this equal sign right here is only true as long as I'm not using x equals 3. Because that would be 0 over 0. So x equals 3 is still a bad guy. It's still an excluded value. It's still not part of the domain. I still have two domain issues, 3 and 5. But I'm not going to get a vertical asymptote at 3 anymore because that canceled out. Instead, I'll get a hole. So we still have domain issues at 3 and, of course, at 5. The graph will have a vertical asymptote at 5, x equals 5, because of this reduced form. But we don't get a vertical asymptote at 3. Instead, we'll get a hole at 3. And the y value, a hole, is just where a point should be. To find that y value, we take this reduced version and plug in that number that we're not allowed to plug in the full version. So I go over here, plug in x equals 3 into this version. 3 plus 3 is 6. 3 minus 5 is negative 2. 6 over negative 2 is negative 3. So now I would graph this guy, forgetting about all this. Graph this guy, he's got a vertical asymptote, x equals 5. Horizontal asymptote, y equals 1. Ratio of leading coefficients. Here's my horizontal asymptote of 1. Vertical asymptote of 5. But now, instead of a vertical asymptote at x equals 3, I get a hole here at 3, comma negative 3. Okay, that's just a brief overview of everything. Like I said, I'll build more videos. It should be popping up in the corners right now, going into more detail on graphing rational functions.